Okay. So let's talk about torque. I'll try to say it the right way, but no promises. Okay, so go ahead and hold your wheel by the wheel. Okay? And what you're going to do is you're going to apply a force. You're trying to hold it steady here after you get the shakes out. Okay? Try to get it balanced there. Apply a force to that. It's not a shaft because this is a shaft. This would be called the cross beam. Anyway, it's called the beam. So apply a force to the beam at a location with your finger.
Ow.
Try to do it at the same time, a couple of different trials, with the same force. And just observe, try to get it established, with the same force, how far does it rotate around? Okay. So now apply same location, more force.
Oh my God.
What do you notice? More rotation, more speed, more of everything. Okay. So I think we talked about it a little bit the other day. When you have something that is just sitting there and then it starts rotating, okay, there's obviously been something that has caused it to start rotating, okay, and you can say it's a force, but it's not just a linear force like everything else that we've been dealing with. Linear forces, a force like that is going to make something accelerate in a line. This is it's like a rotational force or whatever. It's a force which makes something turn, and we call that rotational force. We call it torque. Okay. We don't just call it a rotational force, though that would be really nice. But instead we call it torque for a whole lot of different reasons. So the spelling of that is T-O-R-Q-U-E. The symbol is, of course, Greek. Because Greeks, they're just awesome at coming up with new letters. It's sort of like a T with a fancy hat, and the T is fancy itself. Okay? So, torque is a measure of the rotational force of it. And as we can see, obviously if you hit it with a higher force, then the rotational action goes up. That tells us that torque and force are directly related. Try still same location, less force. Did you get as much rotational action? No. So we would say as the force applied goes up, torque goes up. As force goes down, torque goes down, the amount of actual turning. So whatever this equation is, the torque and the force which is applied are both in the numerators, okay? Because they're directly proportional. So, now, let's try this with another experiment here. Apply your force to the middle of the beam, okay? Same force, see about where it goes with using that same force. Do you not have one? Well, there's not one here. Make sure everyone should be playing. Juan, you with us? Apply it just right there in the middle of the beam, okay? Several times to see what happens. What we're now going to do is we're going to change the distance of where you're hitting the force, okay? The point of action and the pivot point, okay? So you've hit it in the middle there a few times with the same force. Now apply the same force, but go all the way out to the edge. So increase that radius, increase that R. And you should see something change. As you've increased that R, what's happened to the torque? It's gone down? Really? I'm hitting the middle, it goes right there. I hit it all the way out here on the end, same amount of force, it goes around 1.5 times for me. Try in the middle, same force on the outside. Not as obvious. Try it, compare with the middle, try to hit it right there, same force, really close, same force really far out. The hard thing is trying to get the same amount of force each time. Okay, ladies, what do you think? If you go farther away with the same force, does the torque goes up or does it go down? You are correct. Have you ever tried turning something? Like try turning, I don't know, a socket wrench. Have you ever used a socket wrench where you have a wrench and try to turn something? Have you ever, you hold it on the end of the handle. Have you ever tried to hold it really close? Normally, it's a lot harder if you pull it really close. It's a lot harder to get that same torque. So the idea is that the farther out you go, then the more torque you get. In fact, I've got a story about that. When I was dating my wife, yeah, I guess we can say that. When I was dating my wife, my car broke down, or well, it wouldn't start, and I think it was, if I remember correctly, I think it was the alternator or something like that. Anyway, it was like the one thing in my car that I knew how to fix. So I said, okay, and she came pick me up, and we went to the auto parts store, and I got a new alternator, and I came back, and I had to, was trying to take the alternator off or whatever, and I could not get enough torque, I could not apply enough rotational force to undo the bolt. And she says, oh, I've got something in the back of my car to help that. And I'm like, really? What could this possibly be? And she came out with this bar, okay? And you put this bar over top of the socket wrench and extends it out like as long as that bar is. And then it gives you more of a lever distance, more of a radius, and then you can really crank on that bolt.
It gives you more leverage.
Yeah, it gives you more leverage. That's another way of putting it. And that bar has an actual name. It's called a cheater bar. So anyway, so I'm like, well, this girl's got everything. So married her. All right. Anyway, so what we discovered is as the radius, as the distance gets larger, then the torque goes up as well. And so it turns out that those two things are proportional. So we have torque is equal to force times the radius, but there's one other thing that affects the torque, and it's really hard to do this, but I'm going to try to demonstrate it. So yours is going to be horizontal, but for demonstration purposes, I'm going to try to show you with this. I want you to try to apply a force. Go ahead and try it at the end there, but apply it exactly perpendicular. Okay, so for you that would be exactly perpendicular to the beam, and which is pretty much what we've been doing. Okay, so exactly perpendicular to the beam. And see how far that rotates. But then what I want you to do, try to apply that same force, but not exactly perpendicular, but sort of like at an angle. Okay, and to see if as much, if it spins as much or if it spins less. Jesus, follow my instructions. So try it at 90 degrees, and then try it again. It really looks kind of like kind of a glancing blow there. Let's see what happens versus there. If you hit it at an angle, is anybody finding that it's less? It rotates less? If anybody find that it's rotating more? Excuse me. You really like it. That's fine. You can't really do it like this. Okay. So turns out that if you hit it at an angle, if you hit it at any angle other than 90 degrees, the torque actually decreases. Okay, and that you could hit it at an angle which turns out to be like farther away from the point of radius or closer to the radius. Okay, as an extreme example, just to show you, Imagine if you were to apply your force directly along the beam, okay? And see what rotate happens. Ready? Here we go. Nothing, right? Try along the beam outward. So here we go. We get any rotation that way? No. A little bit. If you have it a little bit that way, then it rotates a little bit inward. It rotates inward. Yikes. But 90 degrees there, that is when you're going to have the maximum. So we could spend a whole long time doing this, but suffice it to say that the torque depends on, the third thing, it depends on the angle. And physicists have discovered that it is the sign of the angle between something called the line of action and the radial line, and that's what we're going to look at a picture of here in a minute. Okay? So if y'all promise to play with these when you're bored, then you can hold on to them during the rest of the lecture. Okay? So open up your book to chapter 7, lesson 3. Open up your notes to the corresponding section. Okay, so your book talks about this in relationship to a swinging door. It says forces with equal strength will have different effects on a swinging door. So for instance, if you imagine that we're looking down the top view of a door, and here is the hinge, you could apply a force right here, or you could apply a force right here. If we go over to my door and look at it, Anton, would you mind being cameraman here for a minute? So, when you walk out of my room, okay, here in a few minutes, you could push it over here. And then walk out. Alright? Now have fun with that. In reality, where are most of you going to apply the force?
At the very bottom.
At the end, right, because you're increasing that R distance from the hinge, the pivot point, to where you're applying the force, okay? You can also, just to sort of carry our other example on to a ridiculous level, you know, you could apply the force at an angle right here to open the door, but that's not really going to help out. And here's a biology tip. Whenever you're leaving a room, or maybe say a bathroom or common room, if you're tall, push it up here. Because everybody puts their hands right there. In fact, you can see which kind of gets worn out and stuff like that. But if you put up here, especially during cold and flu season, then people are less likely to put their hands up there. Or you can always just kick it. Have you seen that? Have you ever been to a restaurant? They've got the little thing on the bottom where you can kick the door, pull the door shut. They also sometimes nowadays are putting the trash cans right next to the door. Nice of them to do that. Thanks, Anton. So, yeah, save yourself a little bit of energy, or don't, and you can add it to your workout by always pushing close to the hinge. Okay? But this depends on the magnitude of the force, the distance R from the pivot, and the angle at which the force is applied. So the traditional formula here is torque is equal to the radial distance times the force which is perpendicular. Well, that's not really helpful because sometimes we're going to be pushing at an angle. So this is a much better picture here. This is your pivot point, where they have a nice wrench here. If you apply the force to that point, that's called the point of the application of force. Okay, so you've got this wrench and you're for some reason wrenching it. You know, you're not going to just. I guess this person's not applying it in a perpendicular to get the maximum effect. They're kind of pushing it here. in some of these cases, if you're working underneath a car or inside an engine, you don't have a choice, okay? You have to just apply the force in whatever direction is available. That angle right there, we're gonna call it phi. That is measured between the radial line and the direction of the force, okay? So if you were to extend the force out that way, and you were to extend the radius out here, then we would call that the radial line. And you could measure that distance, that angle right there is called phi. Okay? So there's the picture just expanded for you. If we think about this trigonometrically, you would have a distance right out along here. You can turn that vector with this phi into its two parts. You could have this part right here, which we call F parallel, which is the part of the force which is parallel to the radial line. Or you can have this force right here, which is called F perpendicular. Jesus, let me stand up. This part of the force right here, this component, which is perpendicular to the radial line, and we call that F perpendicular. If you look there, F perpendicular corresponds to F, the magnitude of that hypotenuse, times the sine of the angle, so F sine phi. So F perpendicular equals F sine phi. Another way that they have generated this formula is they've extended the line of this force, and when you extend it, it's called the line of action, and then they draw a radial line which is perpendicular to that in which they connect. It's called R perpendicular. Turns out that this angle right here, phi, is the same thing as that, and you can get at the formula a different way. The moment arm is what we call R perpendicular. It's just the radius that would correspond to where the line of action line would connect. We're not as interested in that. Sort of that's sort of some of the background. And we can, if you want to, I can explain how all that works. But for our purposes right now, we're interested in just understanding the relationship of the formula, which I think we got from hitting the little beam, and that is that torque is equal to RF sine of phi, where phi is the angle between them, F is the force at which you're hitting it, and R is the radius, that distance. So, let's do some problems here. Quick check 710. You've got the four forces. Which one would be the most effective? Go ahead and have a discussion there with the person at your table while I take attendance. Which one of those do you think will be the best? All right, Juan, what do you think? Which one would be the best?
Force 1.
Why?
Because it's farther away from the hinge, and it's perpendicular to the door.
Okay, it's farther away than F4.
F4, yes.
Okay, so I would agree that's why it's better, but it's not farther away than F3.
That's true, but it's perpendicular unlike F3 and F2.
Okay, so it's perpendicular, so that would mean that it's better than F3. Does anybody know what the sine, well, first off, what would phi be in that case? 90 degrees between that force and the radial line. It's 90 degrees. Does anybody off the top of their head know what the sine of 90 degrees is? 1, that's correct. What if it was 88? You may know what the sine of 88 is? Grab a calculator. Somebody else, while they're taking care of sine of 88, let's try sine of 45.
Sine 45 is
Root 2 over 2. Oh, awesome. You know a decimal equivalent of that.
0.7.
0.7. There you go. Thank you. 0.71 actually. Sine of 88 is 0.99. Sure, sounds good. What's the sine of 100? 0.98. Does anybody know if we were to graph every single value of sine, what is the highest it would actually be? It would not be 2. For those of you that have taken pre-calculus, what is the highest value on the sine? It's 1. Okay? Right. So if we have a formula which is torque is equal to F times R times this box here. And this box is the sine of phi. Okay? And the biggest it can ever be is 1. Right? Then the idea is that if it's any angle other than 90 degrees, all right, it's going to be some value smaller. It's going to be like 0.88 or 0.7 or 0.5 or 0.2, which is equivalent to like 88% of this, 70% of this, 50% of this, 20% of that, okay? So it's going to result in a smaller torque, okay? So that's another reason why you can think of why the sine value works properly there. Okay, one, I'm going to argue with you. Force 2 is at a larger R value. It's farther away. So why is it not force 2 for the greatest torque?
Well, like I was saying, you were saying how the force has to be perpendicular to the well, in this situation, the door, in order to have to make the door move. If you're applying the force at the same angle the door is, you won't be doing anything to the door besides just pushing against it.
I challenge you mathematically. What is the angle of phi in F2? Somebody else. What's that angle here? Between this and this? Yeah, it's 0. Okay. What's the sine of 0?
0.
Okay, so it looks like he's right. Because if the sine of 0 is 0, then the whole torque here is going to go to 0. This force right here, F2, results in 0 torque, which will result in 0 rotation. You may be asking, Mr. Goddard, is there a relationship between the amount of torque and how much it spins? And the answer is yes. Wait till Monday. You can learn about that process and about that relationship. So, all right, we have Ryan in here. Any Ryans? No? Okay. Well, Kim, read to us about what Ryan is trying to do here on 7-9.
Ryan is trying to open a stuck door. He pushes it at a point, this is 0.75 meters from the hinges with a 240 Newton force directed 20 degrees away from being perpendicular to the door. There is a natural pivot point in the hinges. What torque does Ryan exert, and how can he exert more torque?
Okay. All right. Well, it's asking what's Ryan's torque, and so I know a formula for that. R F sine phi. Do I know the R? Right there, 0.75 meters. Do I know the force with which he is applying? 240 newtons. Wow, what a beast. Do I know the angle phi between the force of which he's applying and the radius, or the...
Figure it out.
We could figure it out. He's saying 70. That is correct. It is not 20 degrees. It's the distance, remember, here between the force and the radial line, which happens to be, in this case, 70 degrees. So good thing everybody grabbed a calculator. Just go ahead and type that in real quick. 0.75 times 240 times sine of 70, enter.
169.1.
I hear 169.1. How's that sound? What are the units for said torque?
Meters per newton.
Not per, but just meters Newton, although the way that we write it as physicists is Newton times meter. Newton meters. It's not Newton per meter, because that would be Newton divided by. This is just Newton meter. And you might say, do we have any like cool special like unit for that? And the answer is no, we don't. Torque is measured in Newton meters. How could he exert more torque? Okay, more torque. Matthew, what do you think? How could Ryan exert more torque here?
Either push harder or go farther.
Just one.
Okay. Go farther out on the
Radial line.
Yeah,
On the radial line, on the door. That's one answer. Correct. Celine, what is another way in which Ryan could affect more torque?
Maybe go at a more different angle.
Okay, at a different angle. Which way should he apply it? More towards the left or more towards the right? Like, what I mean, like
To the left.
to the left, yeah. More closer to 90 degrees, absolutely. So he could have, more distance, closer to 90 degrees. And Shelby, what's another way that he could affect more torque?
More force.
More force. So beef up those muscles there, Ryan. Try 500 newtons instead of 240. All good answers. All right. So a torque that tends to rotate an object in a counterclockwise direction, so counterclockwise for y'all would be like this, is considered positive torque. Torque that goes clockwise is negative. So just like we have rotations, positive, negative, torque can be positive or it could be negative, okay? Because you could move this wrench this way or you could move it that way, and we need a way to distinguish between 100 Newton meters rotating this way and 100 Newton meters rotating this way. And a little bit later, when we start doing equilibrium problems, because we're going to want an object like a platform to be balanced, okay? You're going to have some torque which is causing it to rotate this way, and some forces which are going to create a torque which are going to rotate that way, and you're going to want both of those to balance out. In order for them to balance out, basically they all have to add up and equal zero. Some are positive, some are negative. Okay. Torque, technically, like we are going to talk about something called the net torque, just like we talked about the net force. Okay, it was with forces we had force 1 plus force 2 plus force 3, and so on and so forth. And then we would say, all right, it's the summation of all of the forces. We're going to have the same thing with torque. The nice thing about this physics that we're talking with right now is that our torque is only going to be, clockwise or counterclockwise. Do that the other way around. Okay, it's only going to be, just either positive or it's going to be negative. When we were adding up forces, we normally had to split that up into the summation of forces in the x direction and the summation of forces in the y direction. We are not going to have to do that with torque. We're just going to say add up all the clockwise torques and then add up all the counterclockwise torques, just add them all up. And, the clockwise are negatives, counterclockwise are positives, and then you'll be able to find an answer, okay? Just to preview, this will not be considered in this class, but for some of you that are going to take calculus-based physics, considering maybe engineering or something along those lines, you will deal with three-dimensional torques, okay, caused by three-dimensional forces and things like that. A situation in which that could apply very obviously would be something in space, okay? Imagine you've got this satellite right here, okay, and you want to move it. You have a thruster on the side, okay, and so all of a sudden the thruster sends out a burst of gases, whatever, and it's going to start rotating, okay. But it also, if that's at an angle like this way, it'll actually could start tumbling, so to speak, okay. So you would have torque in multiple dimensions, not just in a flat sort of like 2D space like we're dealing with. But that ends up to turn out to be some really interesting problems. Believe it or not, the mathematics is not that difficult. It's actually pretty straightforward. So you should never be afraid of something just because of the math. But we are not going to be dealing with that here. We're not going to be splitting up the torque. All right. This question says, which third force on the wheel applied at point P will make the net torque 0? Well, that's kind of a weird way of asking the question. All right, so let's see what's going on here. We have some sort of circular object, a pivot point. Somebody is applying a force on it right there at the pivot point. Somebody else is applying a force right here to the right, and somebody else has their hand here at point P, and they're pushing one of these directions, either straight up or down and to the right, or straight up but not as much, or left or down. And all of these three people working together are going to make it so that this thing does not rotate at all. In fact, you can underline this. This is a vocabulary term for later on. Net torque of 0 means it's not rotating. Or we could say it is in rotational equilibrium. Technically not rotating is not a good definition, because if it already was rotating, it would still continue to rotate. But anyway, let's talk about what these different people are doing. This person right here is applying right there at the pivot point. So which way is this thing going to rotate due to this person? Is it going to rotate clockwise or counterclockwise, or not at all? Jesus? Let's go and drop the chair. Yeah, you can kind of stand in the back there. Yeah, that'd be great. All right, so we have an R value here. I'll put it this way: R value of 0. What's the torque for person A? This person A. The radius of A, he's applying it at 0. What's his torque? 0. It's not going to rotate at all because of this person. It actually might start moving in this direction, but it's not going to rotate. What about person B over here? They're applying a force of F. We'll say that's how long it is, at a distance R. And what is the angle that y'all can see? 90. Okay, so 90 degrees. So the torque due to person B is F R sine of 90 degrees, which we've already determined that that's 1. So the torque due to person B is F times R. And because of them, the object is rotating this way. So let's see if we can make some preliminary conclusion. Whoever's applying the force here at point P, which way do you think they're going to apply the force? Up or down? In order to make this thing not rotate at all. Why down? You could apply a force, all right? Now, if we apply a force downward, that's going to make the object continue to rotate that way. Do you see? Okay, so we're not gonna, so sorry, thanks for playing, but we're gonna have to exert a force upward, okay? Because then if you force upward, that's going to cause the object to rotate clockwise, I guess you could say. Does that make sense now? Okay, that is gonna help us eliminate some options. Okay, so it's not gonna be B, it's not gonna be D, it's not gonna be, the only question is it going to be a whole lot of force or a little bit of force. Basically, this right here is the same amount that this person was applying. Gabrielle, what do you think? Is this person gonna apply a force the exact same amount or even more than this person?
Well, I could be wrong, but if you're just looking at like the vector, then the one that's the longer,
Okay, and why would you say that?
because it also has the force that they're applying diagonally. I don't know if that's,
Hmm.
you can look at that.
Okay, this diagonal right here
We're just
isn't,
gonna ignore it.
isn't doing anything. Yep, it's not doing anything at all.
But
We're just
yeah.
comparing this one versus this one. Now, I drew the direction there. Don't let that fool you. I should maybe make that really small. So it's definitely gonna be that. Okay, we gotta figure out, are they gonna apply with the same exact force
That equals that.
so that it equals 0? Okay, you might think that. Try to walk you down the wrong path here. So you're like, oh, well, this person's applying it and it's going counterclockwise, then this person needs to apply it with the same force to make it go clockwise, right? And so they should balance out, except the torque does not just depend on the length of the force. It also depends on the distance, okay? So in this case, it looks like this point right here is half of the distance. So the torque for person A is going to be, well, the R is 1/2 of the other R. And if I'm going to have it completely equal, just an F times R, if I'm gonna have those two torques balance out, then the force is going to have to be twice as much. Since this person is pushing from half the distance, they're gonna push twice as hard as the person over here in order to counteract and make them balance out completely. So, but you got it now? You see what I'm saying? It's one of those things where you just gotta throw out an answer here, and then you're probably gonna get it wrong, but then in that moment of seeing that, then you're like, okay, totally got it now, not gonna miss it ever again. Anybody else have a question on this? All right, so that talks about torque. Let's summarize what we've learned so far. Torque depends on what? Distance. What'd you say, Hensley? The force applied. And it works on the angle. Okay. You can add all the torques up. Okay. Add them all up. Which one's positive? Counterclockwise, the same as all rotation, the same as omega, the same as delta theta, okay? And then the other clockwise is negative, all right? And we saw there from the end, if you have half the distance, you're going to have to apply with twice the amount of force, okay? All right, you have a couple extra minutes. I'm going to make some copies real quick because tomorrow you're going to do a friction lab, and you need to read through the lab assignment tonight. That way you kind of have a little heads up about what's going on. So you can start packing your things up.